so much, Patrick. It's I'm very happy to be part of this series, and I'm very flattered that there's so many people on different parts of the of Europe watching this. So I'm very pleased, and yes, it's been too long since I've been at Lancaster, so I'm hoping to come back again very soon. Let me share my slides. So now you should see, this is what it looks like outside my window. Not really. This is New Zealand. So let me get my slides going. So hopefully now you should see. Uh,
Yep, all working.
all right, let me just move some stuff. Okay. So, well, thank you so much. And today I'm going to talk about the importance of chunking in language learning. And although most of what I'll be talking about today is not specific to sort of multilingualism or bilingualism or second language learning as such, I think it has relevance to that nonetheless. So when we listen to a foreign language that we're not very familiar with, it often seems like that people speak incredibly fast and that the words blend together. And this experience is an indication of what has been something of an inconvenient truth in the language sciences, namely that our memory and sensory abilities are rather limited when it comes to linguistic input. But these limitations are not just restricted to language. Here we go. It also exists, for example, in vision. And although intuitively it seems that we have sort of very detailed representation of the visual world around us. If you look around, you see sort of you're just sitting there. It feels like you really have a very detailed representation of everybody sitting around you and so on. But it turns out that that's actually not quite the case. And this is something that we know from. Sorry. That we know from cognitive psychology, where studies of, for example, change blindness have shown that what we tend to take away when we're sort of fixating on something with our eyes is rather limited. So let me illustrate that by showing you this picture. So the blinking that you should hopefully be able to see is actually representing what might happen if you move your eyes, because as you move your eyes, you're not taking any input in. Now, unbeknownst to you, actually what's happening here is that something is coming in and out of existence. And if you're going on a plane trip, flying somewhere, then you really don't want this to happen. So you can see here the engine comes in and out of existence. Actually, what happens is that most of the time people have a really hard time finding these kind of changes, and there's all sort of cool experiments. So if you Google this, you'll find all sort of really cool stuff that where things change, and most of the time we don't really notice it at all. But you might be thinking, well, this is just kind of, a trick of the cognitive psychologist. And, if you're sort of in the real world, this wouldn't really be happening. But here's another example of what's called intentional blindness. And so what you can see here is somebody is coming up asking for directions. Then some people sort of rather rudely sort of kind of going between, and then they switch out the person who asked for direction with a different person. And actually what happened is that most of the time people don't really notice that. So more than 50% of people didn't actually notice that this was a different person. So what this means is that the extracted visual information that we sort of take away is really surprisingly minimal. And that's because although we can capture loads and loads of information with our sensory organs, the memory for that in the longer term is rather limited. And that's because new input keeps on coming in, overriding or sort of interfering with old information. But of course, we can remember something. So we can remember sort of the face of our loved ones or many of our colleagues and so on. And that's because we can recode that information, but we need to actually do that in order for it to remain across time. So what about language then? Well, that's what I'll be talking about today, how what Nick Chait and I have called in our Bottleneck applies to language. And so here's a quick outline of what I'll talk about today. I'm going to start to sort of introduce the now and never bottleneck and as a fundamental constraint on language learning as well as language processing. And the solution that learners have to come up with is that they need to learn to chunk the input. And so from this perspective, what language learning essentially involves is learning to process. But how do we figure out what are the right chunks to sort of pick out of the input? And here I'll be suggesting that statistical learning plays an important role in that. And then I'm going to go on to show that if we look at large language models like ChatGPT and so on, it turns out that they also rely on statistical chunking, and actually they do that in a similar way to what we see in humans. I'm then going to go on talking about how the fact that these sort of what I'm going to be focusing a lot on what's called multiword chunks and multiword sequences, and I'm actually going to show you some really new and I think very exciting data that is in press showing that we actually have abstract representations of these multiword chunks. And we do that in a way that might require us how we think about the nature of our mental representations of linguistic patterns. And then finally, I'm going to talk about some work showing how we can use the ideas of chunking to also inform how we look at second language learning. So with that in mind, let me begin. And I'm going to talk about the now and never bottleneck, which are ideas I developed with my colleague from the University of Warwick, Nick Chater. Now, everybody agrees that language happens in the here and now. If you didn't listen to what I just said, it's gone. Now, you can go back and look at the recording, but under normal circumstances, it's gone. Likewise, if you're a learner, if you didn't learn from what was just said, then learning cannot happen. But this actually creates a major challenge for language learners and language users more generally from the nature of the linguistic input. So first of all, the linguistic input is highly transient. On average, the auditory trace of what somebody is saying disappears within less than 1/10 of a second. And on top of that, the linguistic input actually comes at us at a really rapid pace. So on average, we produce about, at least an average English speaker will produce about 10 to 15 phonemes per second, which translate into something about 150 words per minute. But not only does the linguistic input disappear very quickly and yet comes at it at a really rapid pace, but on top of that, our memory for sound sequences is really very limited. So depending on whether you're a Cowan person or a Miller person, it's sort of between ability to remember sort of unrelated linguistic items such as numbers or words that are unrelated to one another is sort of between 4 and 7 of these. So how does our I should also note that if you're interested in sign language, there's similar limitations for sign language as well, although I'll be focusing in my talk today on spoken language. So how does the language system deal with this challenge from this now and never bottleneck? Well, the suggestion that we put forward is that essentially we use the basic memory process of chunking. And to give you an intuitive idea of how this might work, let's do a little experiment. So what I'm going to do here is I'm going to, in order to sort of have this better work over Zoom, I'm going to not do an auditory version of this, but I'm going to do a visual version of it, but the same works for auditory information. So what I'm going to do here is I'm going to show a string of letters on the screen. It'll come up for a very short amount of time, and then there will be some hashes. I'll come across it afterwards, sort of to make sure that you don't have any after image that you can use. And then what I would like you to do is that after the hashes are up, try to recall all the letters that you see in your head. Okay? You guys ready? Okay, here we go. All right, so now try to recall them. Now, if you're like most people, then that is actually a very difficult task because there were 12 letters. And I just told you that that's sort of pretty much beyond most people's working memory abilities. But I don't want you sort of to feel, we just started giving this talk here today, so I don't really want all of you people here in this multilingual group to feel too badly about yourselves. So I'm going to give you another chance sort of to see if you can do better. Okay? So you ready? Okay, here we go. Now try to recall it again. Now, hopefully, some of you, hopefully, perhaps many of you, would actually be able to recall these letters because it was actually the same 12 letters as before, but now they're in a different order, namely one that forms a single word, namely multilingual. And if you code that, you are actually able to chunk all these letters into one single word. And so the suggestion is that when we are processing language more generally, we're doing something very similar. Of course, we're not consciously thinking about how various kinds of sounds go together as such, but we are sort of chunking them automatically into words, into larger units, and so on. And importantly, this is clearly something we have to learn to do. Now, if you didn't know about multilingualism and being multilingual and so on, if you didn't speak English and were able to read sort of words like these, then you wouldn't be able to do it. So clearly a lot of experiences involved with this. And likewise, that goes for spoken language as well. So here's a sort of little cartoonish version of what we have in mind, Nick Chater and I. The solution we suggested in our Never Bottleneck is to engage in what we call chunk and pass processing using multiple kinds of cues. So what you see here is essentially we have time here on the x-axis, and then we have sort of acoustic signals that somebody is talking, and then we have where we are right now in time. And the suggestion is that first we might chunk the acoustic information into some sort of sound-based unit. It can be phonemes, it can be syllables, it can be some sort of something in between. It doesn't really matter as long as you have some sort of sound-based unit. So that would correspond a little bit to before you took the visual.
وينه السباك؟ المحل.
I think somebody is unmuted. All right, I'll continue. So this would correspond a little bit to before when you were watching the visual information on the screen and you were sort of chunking the visual information into individual letters. Of course, what you experience in the first illustration would be would be interference between these letters, making it hard to remember. So therefore, you might chunk it into a larger unit, namely words or word combinations, multi-word combinations. That would buy you a little bit more time. But of course, then you have multiple words that can also interfere with one another. So you do the same process again, and you keep on doing that until you end up with some sort of representation of what was being said. Now, this sort of illustrates the comprehension side of things. And what we are suggesting is that in production, we do something very similar, but in the sort of opposite direction, whereby we start with some sort of idea of what we want to say. We break that down into perhaps intonational phrases, then words and multi-word combinations, then down to some sort of sound representation, and then turn it into articulatory gestures that actually produces what we say. And very nicely, Uri Hirsoon's group at Princeton University have found that using fMRI studies that in the brain that we actually have some temporal receptive windows that kind of correspond to these different levels. So they found that different parts of the brain is sensitive to information at the phoneme level. They did that by essentially comparing forward versus backwards listening in the scanner versus they would scramble the words versus scramble the sentences or scramble whole paragraphs. And you can see there's different parts that seem to be sensitive to that in individuals. So what they found was essentially a hierarchy of receptive windows with different temporal resolutions that consistent with the idea of chunk and pass processing at different levels of linguistic representation. So what this means from the viewpoint of language learning is that language acquisition or language learning is not about identifying the right grammars. That's the job for linguists. Rather, what learners must do is to figure out how to create and integrate the right chunk as quickly as possible before the input disappears. So language acquisition and language learning more generally can be thought of as a kind of skill learning. And this means that learning generally will be local. It's piecemeal, limited by memory within a particular chunking window. It also means that learners will tend to engage or will need to engage in predictive learning. They need to figure out how to apply top-down information and using multiple cues in order to facilitate learning and processing via predictions. And this is something that they gradually develop the ability to do across time. Now, a key implication of this perspective is that multiword sequences, that is, these are essentially sequences of 2 or more words, are crucial for language learning and use. Indeed, corpus analysis and experimental work have shown, for example, that both children and adults are sensitive to multiword combinations. Multiword combinations have been shown to facilitate language learning. And importantly, this means that these multiword sequences provide sort of a bit of a building block for both first language acquisition and processing, but also, as I've suggested in a review article with one of my current graduate students, Serene Wong, it's also important for second language learning. And I'll return to that at the end of my talk today. But also what I'll be focusing on in the remainder of what I'll talk about here is on multi-word combination and multi-word chunks. Well, before doing that, let me just quickly recap of what I've talked about so far. I've talked about how chunk and pass processing is key to overcoming the now and never bottleneck, the pressures that come from sort of the speed, the transiency of linguistic input. And this is relevant both when it comes to vocabulary and language processing skills. An important component of language learning therefore involves learning how to engage in chunk and pass processing, how to be able to do that. And that means that variations in linguistic experience, as well as the nature of the language being learned, can lead to a variety of differences both across individuals and languages. And I think also this is important for thinking about second language learning, because this perspective suggests that variation in linguistic experience and the nature of it will lead to measurable variability in processing, not only across individuals, but also across languages. But this, of course, is theory. So let's move to sort of the more empirical side of things. So if chunks are so important for language learning, how do we learn to chunk the input in the right way? And the suggestion here is that statistical learning plays a key role in developing the right chunking skills. And what I'll talk about here is work with 2 of my former graduate students, Aaron Isberlin, who's at Haskins Lab and at Yale, and Stuart Macaulay, who's at University of Iowa. So let me start with what I mean by statistical learning. And by statistical learning, I mean essentially sensitivity to statistical properties of sensory input across time and space. And of course, here I'm just focusing primarily in the auditory domain, but similar things apply to, for example, sign language. And in this particular study I'll talk about here, we adapted a statistical learning task that was pioneered by Jenny Safran, in which participants are exposed to sort of a continuous stream of syllables, and these actually turns out to be made up of trisyllabic words. And importantly, there are statistical information that provide indications of potential word boundaries. So in this case here, there's transition probabilities between ki and bu, that's 1, and then bu and do is also 1. But at the word boundaries, that transition probability actually dropped here to 0.25. Now, importantly, what Safran has shown in her work is that both adults and infants are actually sensitive to these patterns and can use them to find potential word boundaries in the input. But we wanted to create a task that relied more on memory, again, to sort of capture the chunking abilities that are inherent in how our memory works. And for this, we developed a new task that we call the statistically induced chunking recall task, or SICR. And this task simply borrows from the classic sort of non-word repetition task that's used in language acquisition. Also, for example, in applied context as well, to diagnose people with certain language problems. Also, it plays an important role in studies of reading. And in our case, what we wanted to show was that chunking can emerge by way of statistical learning. And we simply asked people to recall two sets of trisyllabic syllable sequences, and these were either two words from what they had been exposed to before, or they were two random foils that essentially consisted of a random combination of the syllables from the language. And our rationale here was that people would chunk together frequent patterns, and this will show up when we compare the recall of words versus non-words. So for example, participants might listen to like Modipa Kipudu, and then hopefully be able to repeat that back without any problems. And we can compare that with when they hear the foil. So in this case here, they hear a combination of these two, of the syllables in the two words in the previous slide, namely Dibu Moki Padu. And then what we're expecting is that they might actually be able to recall some of them, but they also will make mistakes. You can see it will say Kimu rather than Moki in this case here. And the task is set up in such a way that we simply compare people's ability to recall the statistical syllable trigrams as Modipa Kipudu versus the randomized foils. And the difference between these two is our measure of syllable chunk sensitivity. And so using this, we wanted to compare people's ability to do this in a statistical sort of in an artificial language, like what people typically study in statistical learning experiments. But we wanted to see whether this was actually related to individual differences and how sensitive we are to capturing similar kinds of patterns in natural language. And for that, we first conducted a corpus analysis involving 39 million words of American English. And we sort of pulled out from that, we extracted high frequency trigrams consisting of 3 words. And you can see some examples here: have to eat, good to know, don't like them, is really nice. And then we would ask people to listen to these and recall them, just like you saw before, versus when you take the same words and you randomize them in a way so they no longer fit together in um, in ways that would be reflecting multi-word combinations. So these were actually pseudo-randomized. So in order to avoid high frequency, either bigrams, these are two consecutive words, or trigrams, which are the three consecutive words in these foils. And then the difference in recall between these two types of stimuli was then our measure of multi-chunk sensitivity in natural language. And here are the results. So you can see when we look at the results from the artificial language in the statistical learning task, syllable trigrams, the statistical ones, they were the trigram chunks, they were recalled better than the randomized foils. And we also see in natural language, we see similar patterns. And note that when in the natural language case, you actually had to recall 12 words, which is normally beyond our ability to do that. And that's why you can see that the foils here, people are doing much worse than for the actual trigram. So what this shows is that people are really sensitive to these natural language trigram, and they are able to use that information to have much higher recall performance. And so you can see, we see the same patterns across both artificial language and natural language, with more of the statistical trigram chunks being recalled in both cases. But are these two results related to each other at the individual difference level? And indeed, they are. So what you see here is essentially the Sicker trigram score on the y-axis and the multiword natural language chunks on the x-axis. Then you can see here that the better a participant is at recalling syllable trigrams in the statistical learning task, the more sensitive they are to trigrams in natural language. So from this, we might summarize that what we see here in this study is similar sensitivity to statistical trigram patterns in both artificial and natural language, indicating that these kind of statistical learning tasks provide a useful proxy of the kind of chunking, statistically oriented chunking that we do in natural language. And so we see that statistical learning facilitates chunking in both artificial and natural language, and that importantly, individual differences in statistical learning can predict variation in how sensitive we are to the multiword chunks that appear in natural language. So far I've suggested and provided some evidence for that statistical learning facilitates chunking in humans. But what about other kinds of statistical learners, such as large language models? Now, large language models, of course, are the kind of generative AI systems that many people are using these days, including myself, such as things like ChatGPT, Microsoft Copilot, and so on. And so what a current graduate student of mine at Aarhus University in Denmark, Yngve Nielsen, and I wanted to ask is whether statistical learning in large language models lead to chunking in ways that are similar to what we see in humans. And so what we did is we analyzed some data from humans and large language models to look closer at this. Now, in case you're not familiar with large language models, probably most of you are, but bear with me. Large language models are essentially sort of gigantic versions of what some of us previously have worked with under the notion of artificial neural networks or connectionist models sort of a few years ago. These models that I'll abbreviate them LLMs are trained to predict the next element in given some input, in most cases, at least when we talk about things like ChatGPT. So for example, if the model gets its input, I like to drink, then it might predict coffee as the next item. Now, if it's late in the evening, you might want a glass of wine or a beer instead, but it's still morning over here, so coffee is my preferred choice. And this is the kind of ways that sort of models you may know of or even use, ChatGPT, Copilot, GPT-4, GPT-5, and so on, and others similar to this are using that. Now, importantly, there is an additional step in addition to this training, which is that they're also fine-tuned with human feedback. And in other work that I don't have time to talk about today, we actually have found that this is crucial to make them more human-like in their grammatical language abilities, sort of highlighting, from my viewpoint, the importance of interaction in human language learning. But that's a different talk. Let me instead turn to large language models, and in particular, the suggestion that I put forward with a former graduate student of mine, Pablo Contreras-Callens, and a colleague of mine from Aarhus University, Ross Deans, Christiansen, McClellan, namely that these models, ChatGPT and so on, can be viewed as idealized statistical learners. In that they are able to they rely on huge amount of input that they pick up statistical patterns over this, and they can use this to produce grammatical language. And in a sense, they produce an existence proof, at least in the limit, that it's possible to learn grammatical language from exposure to language alone, albeit tons and tons of it. But moving on to sort of the more pertinent question here is, does these models use multiword chunks? Now, importantly, these models have been accused by some to be essentially sort of stochastic parrots, and all they do is to spew back statistics and so on. But I think this is perhaps a little bit too unnuanced in that humans too are highly dependent on statistical patterns, and also as we found and many others have found, we also rely on these multi-word combinations. So in a sense, perhaps we are also a little bit of a stochastic parrots ourselves. And so what we wanted to see is just know, are LLMs more like stochastic parents than humans? And one way we decided to do that was to look at their use of multiple chunks, both humans and LLMs. And there's a wonderful sort of combination of two corpora that provides like a really useful way of testing this question. And so for our human dialogues, we analyzed the empathetic dialogue corpus, which essentially contains chat conversations between over 800 participants, and then we're structured to carry out conversations from an sort of emotionally laden prompt, such as, for example, they might be given that, oh, what you should talk about being afraid, and here's the situation. You should talk about the speaker felt this when I've been hearing noises around the house at night, and then they will sort of have a discussion about that. Bit artificial perhaps, but at least they were sort of looking, they wanted to look at how people expressed emotion and so on in conversations. Now, importantly, there is a parallel corpus of essentially getting two large language models to talk with one another, namely two versions of GPT 3.5 Turbo. And these models were giving the exact same prompts as the humans, and then asked to interact with one another. Now, importantly, the reason why we use LLM to LLM or human to human is that oftentimes when we engage with large language models, there's not really a natural conversation we're having. What we're often asking for is, how do I code this in R? How do I code this in Python? How many people live in this country, and so on. That's not really sort of a normal conversation. That's why this is a better way of looking at sort of more sort of conversations between LLMs in ways that are better parallel how humans normally converse with one another. And importantly, they used exactly the same prompts as for the human, so we have a fully parallel corpora. And so in order to sort of look at the presence and use of multi-word chunks, we focused in our analysis on 3-word chunks. And we use a very sophisticated measure that was developed by Stefan Gries. And that measure essentially incorporates 8 different statistical variables that capture different aspects of multi-word chunkiness. And I don't really have time to get into that. But let me instead show you what we found. And what we found was, so what you see here is the mean multi-word unit scores for LLMs and for humans. Each dot represents a sentence, and the gray lines between them denotes the prompt share between humans and LLMs. So that are kind of connected up in this way. And so what you can see here is actually that humans are slightly more prone to using multi-word chunks compared to LLMs. And in fact, this difference is significant, but and that's because we have so many data points. So at least if one wanted to take something away from this, it turns out that humans might be more like stochastic multi-word parrots than large language models. Although wouldn't necessarily put that too much weight on this difference, but at least there's no difference between the two. I think it's a more solid takeaway. It turns out though that when we sort of dug into the multi-word chunk measure in a bit more detail, we found that they seem to be using the statistics to capture these multi-word chunks in slightly different way. And so what you see here is the probability of an utterance being human-generated as a function of each of the 8 statistical measures that go into the how we sort of picked out multi-word chunks. And so what you can see is, so here what I've highlighted in green are the ones where we see that LLMs use more than humans. And so in this case here, some measures turns out to be more characteristics of how LLMs sort of extract multi-word chunks. And these are token frequency, type frequency, 1 and 2, and forward association. Whereas in other cases, we have for humans showing a different pattern, so that humans tend to rely more on backward association and 2 different types of entropy. And then we have one case here where there's really no difference dispersion. So to recap here, so there has been a lot of debate about whether large language models are merely sort of blindly parroting back fragments of language in ways that sort of differ from the sort of very celebrated use of language that we see in humans. And of course, oftentimes that's been taken to be that some have argued that we need sort of specific biological structures in order to be able to use language, and that we use language in sort of very principled ways. However, a lot of the work in language acquisition have sort of kind of cast doubt on that, including the work on multi-word combinations that we see here, suggesting that when it comes to production of language, multi-word chunks plays an important role for both humans and large language models. But we also see there are some subtle differences in the statistical makeup of how humans and LLMs use multi-word chunks. But I think it does underscore that LLMs are not mere stochastic parrots, at least not when it comes to their use of multi-word chunks. Now, sometimes how they use them in terms of their semantics and grammatics is not as good as human, at least currently. But we do see that at least when it comes to just the pure sort of structural use, then humans are using more chunks. But given that we've seen that multi-word sequences are sort of important for both humans and large language models, But there's still we're looking at them at a very sort of concrete level. So this is sort of specific combination of words. But might there also be a more abstract representation of multi-word chunks that we have as humans? And this is some new exciting work. We're also with Yngve Nielsen from Aarhus University that is sort of in press at the moment. So I'm very excited about it and look forward to hearing what you think. And so what we did was in a series of experiments, we looked into possible abstract representation of multi-word chunks using the method of priming. Now, priming has been widely used in cognitive psychology to provide evidence of sort of mental representation of whatever it is people are trying to prime. And in psycholinguistics, it has been used to prime syntactic structures, such as the passive construction. If you come across a passive construction, you're more likely to use it again shortly thereafter. And so what we are relying on here for this experiment is sort of what's sort of very elegantly put by Holly Bottleneck and Martin Pickering in their BBS paper from 2017. They talk about priming and saying that if processing one stimulus affects subsequent processing of another stimulus, then these stimuli share some aspect of representation, meaning that there's some sort of mental representation of that's in common to those two. So that's kind of what we took advantage of. Now, for the purpose of our study, we used a multi-word decision task. And this kind of task had previously been used to study the processing of multi-word combinations in isolation. But here we wanted to look at whether a specific combination of parts of speech items would prime a similar subsequent parts of speech sequence. Because that would indicate that the parts of speech sequence at some level would be represented, at least the sequence of those items. That is, we compare target responses for a particular parts of speech sequence when they were preceded by a similar parts of speech sequence before. Now, importantly, as you can see here, so of course people didn't see verb determine a noun, for example, but rather what they would see on the screen is take a break, and then they had to respond to that. And importantly, you can see there's no overlap in words, but it's the same parts of speech sequence, know this girl. And we compare this with when the target is preceded by a control where there's no overlap in words or in parts of speech sequence. So here we have adjective, adposition, pronoun. So we were expecting that if there is some sort of representation of this sequence, verb determined noun, then we should see faster response for know this girl when it's preceded by take a break than compared to when it's preceded by many of whom. That's sort of the rationale here. So here's sort of a sort of cartoon version of the task, the multi-word decision task. Essentially what people are asked to do is that they're shown a three-word sequence on the screen, and then they're asked to judge as quickly as they can and as accurately as they can. Does this three-word sequence form a possible combination of words as part of an English sentence? So, for example, if you see take a break, you would hit yes, it's possible. Whereas if you see full the out, so that's sort of the foil, you would say no. And importantly, this is modeled on the classic lexical decision task that's been used in many studies, where you see a word on the screen and you have to say, is this a real word of English, yes or no, or whatever the language you're looking at, of course. Now, and I should note that this and the subsequent experiments that I'll talk about here were all pre-registered. And here you see the results, that indeed you can do this kind of priming. So what you see here is reaction time in milliseconds on the y-axis. And here we see primed versus non-primed, and there's a difference of 20 milliseconds here, meaning that we get a priming effect. And so lower here means faster. So what this suggests here is that we do have some sort of abstract representation of multi-word parts-of-speech sequences. But there is a caveat here. This kind of priming could be perhaps explained in terms of standard structural priming involving abstract syntactic trees. So at least from my perspective, this is not particularly exciting. But we push this a little bit further, namely to look at non-constituent multi-word chunks. But previously, what I showed you were constituent multi-word chunks. And this is because multi-word combinations come in many different forms, and some of them are in fact non-constituents. So for example, we have non-constituents like a lexical bundle, So here we have in the middle of, which is a lexical bundle. It's not a constituent because it's missing in the middle of the night. It's missing sort of the noun phrase in this case here. Now, importantly, Tremper et al. Found that in the middle of is read faster than in the front of, indicating that there's some sort of, might be some sort of representation of this. But we wanted to see whether there might exist a more abstract representation of non-constituents. That is, are non-constituent multi-word parts-of-speech sequences also mentally represented, which I think would be quite interesting if that was the case. And so if non-constituent multi-word parts-of-speech sequences can't be primed in a way we saw for constituent sequences, then this cannot be explained by syntactic trees because you wouldn't expect them to sort of what they call license in the middle of. So we conducted sort of the same experiment, created another set of stimuli to look for possible priming of non-constituent structure. So again, we have parts of speech sequence, knew that she, so this is not a constituent, so this is verb, conjunction, pronoun. We want to see, will this prime another similar parts of speech sequence, wondered if you, compared to the control trial when we have a different set of parts of speech elements occurring before the target. And indeed, it can be primed. Non-constituent parts of speech sequences can be primed. And that suggests that we are in some way representing these sequences mentally. And here you can see compared to the constituent priming showed you before. So if anything, there's actually a slightly larger priming effect for non-constituent parts of speech sequences. Now, this, of course, we were quite excited about this, but to make sure it wasn't a fluke, we replicated our first non-constituent priming result in another experiment, also pre-registered, with different stimuli and a different participant population. And again, we found that, in fact, non-constituent sequences of parts of speech elements can be primed. So we're very happy to replicate that. But there was perhaps one other alternative explanation for these results, namely is that perhaps it's just that when you have the same parts of speech elements occurring twice, that you get some facilitation of that, not because of the sequence itself, but simply because you're repeating the same parts of speech elements. And so to rule out that our results were not simply a matter of priming the individual parts of speech element independently of their sequential order, we compared non-constituent priming to when the order of the priming of the parts of speech sequences was simply reversed. So that should, if that alternative explanation was true, then we should see no difference, yet we still get the same priming effect as before. You can see the priming effect here. The verse primes actually makes it worse. So just repeating the items does not actually facilitate processing. It has to be in the right sequence. Now, during the review process, one reviewer suggested that, well, perhaps what's really going on here is actually these non-constituent parts of speech sequences, they're actually activating larger constituent ones that would correspond to a tree. So for example, and that would be through a process of what refers to as sort of structural prediction. So for example, if we present our participants with live in A, that's a part of a constituent, what happens is that actually participants in their mind completes this as live in a house, which is sort of full constituents. So just to show this in terms of parts of speech, so we have verb, preposition, determiner. What actually is, so where we were sort of thinking this would be sort of a flat sequence of parts of speech items where the order of course matter. The sort of the more classic syntactic perspective would be that, well, actually what's happening is that this is actually sort of essentially activating in the minds of people a larger whole unit, namely verb, preposition, determiner, noun. So we get sort of the noun in there. And so if that's the case, then the prediction from the structural prediction perspective would be that if non-constituents, let's call them parts, automatically activates full constituents, which is certainly a possibility, then response times should be the same whether whether the non-constituent is primed by part or whole. And that is whether the question is whether, and that's independent of whether the priming is with a part or a whole constituent, because both would activate the same representation. And this prediction is actually not borne out, and I know these results are a little bit complex to look at, but overall, let me just give the overall point here is that overall responses to part targets were faster than whole targets. But let me break this down for you so you can see. So what we have here is focusing on the part targets first. And what you can see here is that that responses to part targets were faster following part primes than whole primes. So here we have the whole primes. So it's not the case, we would expect that that would not be the case if you automatically activate the whole when you have the part. And when we look at the whole targets, we see that whole target responses were faster following whole primes than part primes. So what this means is that like primes, like non-constituent parts of speech sequences are better primes for non-constituent parts of speech sequences, and similarly constituent parts of speech sequences for constituent sequences. And this is inconsistent with the sort of proposed alternative explanation of this sort of a structural prediction mechanism, because exposure to non-constituents should activate the full constituent automatically, making parts and wholes representationally equivalent. So to recap here, and we actually also replicated the same results both in analysis of conversations as well as in eye tracking data also. So we found evidence that multiword parts of speech sequences can be primed, and remarkably, this also applies to non-constituents. And I think this calls for a reappraisal of how we think about syntactic priming. So rather than thinking of linguistic representation in terms of syntactic trees, it might be more useful to think of them as mental representation of linguistic structure, think of the mental representation of linguistic structure as corresponding to processing history. And if so, then perhaps non-constituent parts of speech sequences might function as something like processing glue that connects patterns for different constructions or constituents with one another. And just to sort of give you a cartoon version of this, so what you see on top is sort of the interposition of the lexical chunk top of the that provides sort of that glues together two constituents on the top and the tallest mountain, so to produce the on top of the tallest mountains. And the bottom shows that this is done through the interposition of the non-constituent structure noun preposition determiner that glues together these two other ones through a proposition. But let me finish up here by talking about chunking and second language learners. So are L2 learners sensitive to chunking in the same way? And we actually have, this is work, one of the specific work I'll talk about now is with a former PhD student in information science here at Cornell University, Gabriel Culbertson, who's now at Google. But more generally in my lab here at Cornell, we have sort of several ongoing studies looking at multiword chunks in L2, including at how we might leverage chunking to improve L2 learning. But first, we felt we need a better way of measuring L2 proficiency in the context of real-world language use. And what we did in this study is we used utterance recall to measure L2 learning as a way of capturing L2 learning, L2 processing in real time, and thus be some under the pressures of the now or never bottleneck. And the thing is that most standard L2 proficiency tests, they don't really measure L2 real-time language skills, and we wanted to come up with a proficiency measure that would sort of better capture that. And so this study involved 100 L2 Spanish learners that had English as their L1. We used Spanish recall as a way of measuring their proficiency in the L2, sentence utterance recall in this case. And utterance recall requires learners to be able to chunk and pass process in order to get the meaning of the utterance before they can repeat it back, or at least repeat it back as much as they can. And that's because the utterances that we use would be too long to be able to recall from memory. And we also looked at their sort of chunking ability in the native language, the L1, for comparison baseline. And then as a sort of more standard test of their proficiency, we used the sort of standard multiple choice test where they listen to a short audio clip and then they answer multiple choice test. And what we did was we took some elements from the national Spanish exam, and then we also asked them to self-report their proficiency. And then our dependent variable in this study was a sort of variation on what's called the listening summary translation exam. And in our case, we had people translate short excerpts from Mexican TV series into English. And that's meant, so the idea of the translation task here is that it captures your ability to listen to something, understand it, and be able to use it actively in the translation. And what we found was that, and here you can see correlation results after Bonferroni corrections for multiple comparisons. And what we found was that L2 recall was by far the best predictor of translation ability, much better than L1 recall, also better than the more standardized way of measuring their language ability and self-report. And just here you see the correlation patterns where we had the ability to do translation on the x-axis, and then we see the Spanish recall on the y-axis. So what this shows is that the better the learner's L2 recall is, the better they are at the translation task, and the L1 recall didn't correlate in this case. So to recap, Chunking at the sentence level provide a good predictor of real-time proficiency, at least in this case, and we've done some other follow-up work subsequently that kind of confirms that for other languages such as Chinese. And so more generally, what this suggests is developing L2 chunking scale is key to doing this, and that's why it's useful for our purposes. In Bottleneck and I have also argued that L2 and others have too, that L1 and L2 learners might use multiword chunks in slightly different way, but in both cases it facilitates language processing and production. And in particular, in some modeling work, Stuart McCauley and I have shown that L2 learners rely more on simple frequency rather than statistical learning. And it would be interesting to apply some of the more sophisticated measures that I talked about earlier that we used to look at large language models to L2 language as well. And so we are also now working in the lab on how we might improve L2 learning by improving chunking in the L2. So let me quickly conclude here. What I've suggested is that language acquisition and language learning more generally fundamentally involves learning to process, and that's a way for learners to overcome the bottleneck that creates a formidable challenge for real-time language use. And in this case, chunk and parse processing, or chunking in particular, is a key mechanism to overcome the pressures from the now and never bottleneck. And we've seen that statistical learning can play an important role in discovering and using multiword chunks as the building blocks of language, and then also includes what we see in large language models. This also means that chunking is highly important for L2 learning, we think, and that L2 learning might be improved by strengthening statistical chunking skills. And I think it also opens the sort of intriguing possibility that this might also be something we can do at the more abstract level. For example, utilizing the new data that we have from parts-of-speech sequences, multiword parts-of-speech sequences, to train people on that. But that's something for future studies. And with that in mind, I want to thank you all for listening. I'm happy to take your questions. So I will.
Thank you very much. I'll just stop the recording now.